There we go. Creepy screen. Hello, everybody. Hello. Thank you. Welcome back. Lots of happy chatter today. Are we having a good day? It sounds like it. Just get this positive vibe. You're not having a good day?
I slept a lot.
You slept a lot. That makes for a great day. Too much. Is there such a thing? Really? There is?
8 p.m. to 10 a.m. this morning.
Boom. Drop the mic. That's awesome. You go. You was late for some stuff, but it was worth it, wasn't it? Yeah, I actually stayed up later than usual last night because I wanted to watch This Is Us and find out how Jack died, finally.
No spoilers.
That, I will not tell you, but they did a good job of dragging it out. Although I found it very, I'm going to say this word wrong, macabre? What's that word? Macabre? It's one of those words I've read in books, but no one has ever used around me, so I don't know what it should sound like. Macabre? Is that what it is? Where'd the R and the E go?
It's like French.
Okay, well, I thought it was macabre to show that particular episode on Super Bowl Sunday. That's all I'll say. Macabre? Really? This is going to bother me. I was further off than I knew. I'm sorry, but yeah. So yeah, I didn't sleep as much as I should have. But I've got my due, and I will persevere. Right. So we had a quiz to look at. Let's chat about that briefly. 3 questions this time. You should be able to get back into Blackboard and see your answers, and you should be able to see my answers. So in what kind of designs, longitudinal designs, does one need to worry about this time-related convergence, age-related convergence, the stuff we've been talking about? When time is between and within. And you would know that when people walk in the door in your study at different points in their time, in their ages, in their grades, in how long they've had whatever condition you're studying, and so forth. So why didn't we worry about this at all last semester? And how do you know in the future if you need to worry about it? What did you write? This is what I wrote, but what did you write?
I said we were looking at balanced data with all people starting at the same time.
Yes, all people starting at the same time point. Balance, like if it's unbalanced, you can get a little bit of between person because of that, but yeah, it's the same people starting at the same time is the key. And I did that on purpose so that we could just talk about getting the fixed and random effects of time. In other words, time was entirely within persons. So if you are handed a data set off the street, let's say, you find it in like Storage Wars or something, and you don't know anything about this data set, how would you know if you need to worry about this? I had my idea. You can run an empty model on time and find out how much of its variation is between persons versus within persons, as indicated by our friend the intraclass correlation. If you don't have to worry about it, your ICC will be what? Something small, 0. 0 or as close to it as possible. That means time is within. It means it can only have a level 1 effect, and you don't have to worry about how to represent it between persons. If that is not the case, then you have to worry about it. I did age at the beginning of the study or time at the beginning of the study so that I didn't confound missing data patterns with cohort differences, but that may not always make sense. So it's just keep in the back of your mind that you have to worry about between and within time in these instances. And what else did I ask? Oh, yeah. How would you interpret a contextual effect of age in an accelerated time model using age as the level 1 metric at time? So this is straight out of chapter 10. Contextual effects are cohort effects. It's the idea that after controlling for your current age, it matters when you were that age, that there's an extra contribution from baseline age above and beyond current age. And I asked you last time, how many of you found that confusing? And you're like, yeah. And I agree with you, and that's why I say just put in time. Don't do it that way. It's easier if you just put it in time. But that's what it means when you have a contextual effect. So How did that quiz go for you? Pretty good? Broad strokes? Yeah, that's really what I want you to take with you is broad strokes, because if you know like sort of the context of the problem you're dealing with, you can always go back to your notes and get the nitty-gritty and the details, but the broad strokes will carry you through recognizing how to deal with longitudinal analysis problems in the future. So I will take a look at those. Homework 2, I just put up a couple hours ago. That is ready for you. So that will be this type of analysis, an accelerated longitudinal design, although no one will be dying. It won't be macabre this time. Really? I'm still on that. Macabre. That's okay. I digress. So we have some new stuff to do today, unless anybody wants to talk about anything else before we dive in. Nobody wants to talk about anything else? We're good? Okay, well, if you do have questions about anything and you're too shy to speak in front of everybody, please feel free to email me or stop me after class, and I'm also happy to arrange individual office hours too if you're uncomfortable talking in front of other people. Just keep that in the back of your minds. I'm happy to help clarify things if I can. So the topic that we have here, Lecture 3, this is the #1 thing people screw up in multi-level modeling, hands down. You know the fancy conference that I went to in Utrecht, where I got to talk and they paid for my trip and I was like, yay, remember that story? A lot of people who presented at that conference committed this cardinal sin. And it was like a conference on multi-level modeling and they still screwed it up. I'm telling you, this is rampant. I have seen many well-intended tutorials in what I would call content journals, like journals that are area specific, where somebody writes how to do multi-level modeling in blah, blah, blah data. And a lot of them make this mistake, have this problem that I'm going to tell you about. So this is it, folks. You are never going to do this in your life. You are never going to get this wrong, because I will roll over in my grave if I find out that you do. The cardinal sin goes by my definition. I call it smushing. Now, I do know, as someone told me in a workshop once, that if you ask the Google what smushing means, there's an entirely separate definition brought to you by the folks at Jersey Shore that I do not intend. So that's not the kind of smushing I'm talking about. But it was foreshadowed by the last topic, the idea that if you have a level 1 variable that has both between variance and within variance, you have to care about each part separately. That's the big picture. To not do so is to smush those two sources of variation and their effects together, and that is smushing and that is bad. So we're talking about time-varying predictors, starting off with the case of within-person fluctuation, because this is the simpler of the two. When we get to the point of talking about time-varying predictors and models of change, that's where it actually requires a multivariate model instead, and so that will be coming later in the semester. So time-varying predictors that fluctuate is what we're talking about. So these can be used in models of within-person change or within-person fluctuation on the outcome side. So the idea for modeling time is that once you've put in the right model for time, meaning the one that's best supported by your data, fixed and random effects, the residuals that are left should not have anything to do with time. So time is actually not going to be part of this lecture. I'm going to show you pictures that instead of having time on the x-axis have some other variable there, because we're at the point where after putting in whatever effects of time you need, the residuals should not have differential variance or patterns across time. So time-varying predictors, most of the time, have two kinds of variation in them. Just like time-varying outcomes have some of the variation that's between persons and some that's within, any predictor that's measured over time likely does too. So for example, if I think about the idea of stress and health as a motivator here, within persons, if I measured stress repeatedly across days, I'd find that sometimes we have more stress than usual. And if I asked somebody, on average, how stressed do you think you are relative to other people, some people would say they're more stressed than other people. So stress can have both levels of variation if you measure it longitudinally. And we can quantify how much variation a time-varying predictor has at each level the same way that we do with an outcome, an interclass correlation. So if a predictor measured at level 1, so do we need to go back over vocabulary? Level 1 is within, is longitudinal, is residual variance. If a predictor measured at level 1 has an interclass correlation greater than 0, it has at least some kind of between. So even though you're thinking of it as a level 1 within variable, to the extent that it has variation that's between, to the extent that its interclass correlation is bigger than 0, it has the potential to have a between person effect. Likewise, to the extent that its interclass correlation is less than 1, it has within variance, it has the potential to have a within person effect. So if I have a variable like stress, where some people have more stress than others on average, those between person differences in stress can predict some kind of between person outcome variance. To the extent that some days I feel more stressed than others, that within person variation can predict within person variation in an outcome. So having variation at each level is a necessary prerequisite to having an effect at that level also. So it's not just where the variable is measured, but what kind of information it contains, whether it's straight within, straight between, or some combination thereof. Most of the time, time-varying predictors are some combination thereof. So hypotheses then, if we think about relationships between variables and how we phrase these types of hypotheses in a longitudinal design, it has to be more specific than in a cross-sectional design because you have to talk about the different levels at which your hypothesis could be true or not true. So for instance, stress and health between persons. People who have more stress than other people may have worse health than other people. That could be found in a cross-sectional study, but it could also be found in a longitudinal study to the extent that both of these variables show between person differences. Within persons then, when I have more stress than usual, my health may be worse than usual. So there's a negative relationship between stress and health, or more stress equals worse health. Yeah, sickness, you know what I'm saying, right? Badness. Stress is bad for you. Bad for you between persons, bad for you within persons. Both of those could be true. You might also see effects in opposite directions. So a classic example I borrowed from some book, I forget what, exercise and blood pressure. If you think of blood pressure as a proxy for physical health, people who exercise more probably have lower blood pressure. But when you're actually moving, your blood pressure is higher than when you're sitting still. So the relationship is different at different levels because it means something at different levels. And so these variables have different meanings at different levels and they have different scales at different levels. So we would not expect between person effects to be the same magnitude as within person effects for both of those reasons. And we have to be able to differentiate them in our models. So there are 3 kinds of fixed effects that time-varying predictors can have. I've grayed out this last one because we're going to delay talking about that until we get our hands on the first 2. But the first 2 here, and I'm trying to use color coding to make things easier in the equations to keep track of, but the green here, level 2, between person. Do people that have more of an X have more of a Y? So it's people who as the prefix for the statement. And these are on average across time. These are cross-sectional effects. If so, then we would expect those between person effects of a time-varying predictor to capture level 2 random intercept variance. Within persons then, at level 1, if you have more of a predictor than usual, do you have more of your outcome than usual? If so, then that within person effect should account for residual variance at level 1. And we can compute pseudo R-squares to talk about the contribution at each level. So how do we operationalize these ideas in a model? The way that I'm about to show you is admittedly antiquated. The way that I'm about to show you is what people came up with first, and there's some research suggesting that it is no longer the best way to do it. However, it's a common way to do it, and it will always work. Whereas more complex methods sometimes will not converge. So we're starting here, And then later in the semester, we'll look at the more complex version of the same ideas. But we start out by taking our level 1 time varying variable and literally carving it up into the two kinds of information that it carries. So at level 2, we are going to put in the person's mean across time as the indicator of the between-person variance in the predictor. That person mean needs to be centered at a constant so that 0 is a meaningful value, just like any other predictor would be. At level 1, there are two choices as to how you can put in your time-varying predictor. What is known as group mean centering or person mean centering in this context versus what is known as grand mean centering or really just constant base centering. So it's the distinction between these really is, are you centering using a variable or are you centering using a constant? That constant could be no constant, meaning leaving it uncentered. So these choices apply only to what you're doing at level 1. You can center level 1 at a variable or a constant. At level 2, you're only centering at a constant. If 0 is already a meaningful value in your person mean, you don't have to center if you don't want to, but it's about keeping the intercept interpretable. In longitudinal data, by far I prefer the first method here, and so that's where we're going to start, person mean centering, by far. In clustered data, I go the other way. I prefer grand mean centering. So there's not necessarily a right or wrong way to do this. These can yield equivalent models with rearranged parameters, but their interpretations of the parameters differ depending on how you set this up. So I want you to know exactly what you're asking the software to do when you set up your model these ways. But the big picture here is that you can't just use the original, I'm going to need that, the original level 1 variable. You're taking that original variable and you're carving it up into two new ones instead. A between-person version, person mean, and the within-person, which we're going to do person mean centering with. So any time-varying predictor that has an ICC between 0 and 1, we need to do this for. So this is what it looks like. We take the person mean of our variable and we center it at a constant. So let's say that we pick the sample mean. Then this new variable that I'm calling PMX here, that's what I'm going to use in my equations to represent this idea. If it's positive, that means you have more of this X than other people on average. If it's negative, you have less than other people on average. Analogously, the predictor that's going to go into the level 1 model, which I'm calling within person X, is the original time varying X, so XTI, that's how you know it's the time varying one, minus the person's mean. So the I indicates that it's a person level variable. The within person is time varying, then gets the TI. So in this case, we don't have to center at a constant because we're centering at a variable instead. So within person X is 0 whenever you're at your mean, whatever that happens to be. Whatever that happens to be shows up in the level 2 model instead. So within person X being high, being positive, means that I have more of whatever this is than usual. Being negative means I have less. And that's exactly how I would talk about it. We would say people who, to talk about the green effects up there, and when you do more, to talk about purple. The equations would look like this. So for simplicity here, I've taken out any effects of time, but if you needed fixed and random effects of time, you'd already have them in here, and then you'd add the stuff that I'm showing you here. So in the level 1 model here is within person X. This is how it is made, just to remind you. In the level 2 model then is person mean X right here, and this is how it's made. And the interpretation of these new effects is very straightforward. Because the purple has only level 1 variation in it, by subtracting the person mean, we've taken all the between person variance out of it. Purple is only level 1, is only within. So the fixed effect that it gets in the model is the within person effect, the end. Green has only between person level 2 variation because it's the person's mean. So because it only has level 2 between person variation, the only kind of effect it can have is level 2 between. So person mean X carries the between effect, within person X carries the within effect, the end. That's why I like this. You can't screw this up. If you leave either one out of the model, you're assuming it's 0. Just like any other predictor that's not in your model, you're assuming its slope is 0. So the green, gamma O1, is the effect of having more X than other people on average. Gamma 1O here is the effect of having more X than usual. These two predictors are orthogonal. So you can put them both in the model at the same time because they both have a different job to do. They work at their own unique level. So what we've done is a brute force analog of what we're asking maximum likelihood or residual maximum likelihood to do for us on the y side. So YTI here, note that the purple and green smush, I'm going for color coding here. Can I get extra credit for that? Thank you. I'm shameless, aren't I? Look, I put together a slide. I want a round of applause. Yay me. So yes, we started with this observed variable, and we estimate at first an empty model for it. And SAS, or whatever program we're using, coughs up a random intercept variance, and it coughs up a residual variance. We let the program do that for us. It found those variances. It decided how much they should be based on what maximized the likelihood across observations. We're doing that ourselves instead. We took this X and we carved it up into, I'm drawing these as boxes because these are observed variables as opposed to things that the program found, latent variables in circles. So we have person mean X, which is the analog to random intercept variance, and we have within person X, which is the analog to residual variance. We just made observed variables to capture those sources of variance rather than letting the model do it as variance components. Now, when I say it that way, how many of you are thinking, well, why don't we just have circles for both of them? Like, doesn't this seem sort of arbitrary that one side gets boxes and one side gets circles? Anyone? You're like, I don't want to guess. It seems kind of arbitrary to me. And that's the rationale between the newer way of doing things, which can't be done in R from what I understand, unless you can trick it into being a structural equation model. But this is what I call multivariate multi-level modeling, or what some people call multi-level structural equation modeling. It's the idea that we let both variables get partitioned by the model. Rather than creating boxes to represent each source of variance on the predictor side, we let the model estimate those sources of variance instead. So I'm teaching you the boxes version first because you can do that in more software packages and it's guaranteed to converge. Whereas if you're estimating 4 things instead of 2, you can see how quickly that might go haywire if you have lots of variables in your model and lots of variances to be estimated simultaneously. So there's some readings on your list down in the multivariate section that have done simulation studies looking at when each of these approaches may or may not work better. Boxes will work better if you have a very small intraclass correlation in your predictor. It's hard to estimate variances that are little, generally speaking. Estimating the variances will give you less biased effects, particularly in the level 2 model, but it comes at the cost of more noise. So the estimates are noisier, they bounce around more than if you have boxes. So there's pros and cons either way. Using the boxes? I haven't, but I think that day is coming. I think that there's still so much, multi-level SEM is like the newest, shiniest toy in the toy box that not everybody's played with it yet, so I don't think that, I haven't had much pushback, but I think that day is coming within the next 5 or 10 years. Have you had pushback? Okay. Just saying, there isn't, I mean, there's some research suggesting the boxes don't work as well as the circles, because that's like the whole basis of structural equation modeling, making latent variables and things like that. But there are situations in which trying to estimate too many things leads to none of it being estimated well. So there's always a trade-off. Least selfish, heck yes.
If your box variable is a variable
No, I would say this distinction is irrespective of whether you have an objective measure or a subjective measure, because there's no measurement model in here. That's why I put multi-level SEM in quotes, because people will call it this, but to me that's wrong, because there's no measurement model in here. To me, a structural equation model has latent variables as defined by a measurement model, but some people would call this random intercept a latent variable, and so they call it multi-level SEM. Yes, that face, that's me. So I give you the pragmatic advice, right? If in your job talk, you are doing multi-level SEM, damn it, that is what you are doing. Put as many adjectives that sound fancy in front of what you're doing as possible. Once you're on the other side of that, then you can keep it real. No, it's a multi-level model for multiple variables at the same time. I call that multivariate. That's what I call it. But we're not there yet. We're going to do it univariate style first to get the concepts down, and then we'll do it multivariate style later in the semester, because it requires M+ software instead of SAS. So we are making boxes to represent the same constructs that are represented by variances on the y side. So person mean x is to random intercept variance at level 2, as within person x is to residual variance at level 1. You got me? And now the energy has dipped. Wake up! Heather, wake up. I have eyes, I can see. Can you imagine if this was a 3-hour class? Every semester I get somebody who says, I wish it were 3 hours because that's so much more convenient. It's like, do you want to listen to me for 3 hours? Because I don't want to talk for 3 hours. I used to do ICPSR workshops. You know that, I forget what it stands for. It's the thing run out of Michigan, and those are 5 days a week, 8 hours a day. Can you imagine? And those are really tough, because by like 1 in the afternoon, everyone in the room is done, right? You can they have checked out, you can see it, but like we're all contractually obligated to be there. They're paying me, so I just keep talking even though no one's listening, and it's just like, it's horrible. But yes, the human mind is not meant to absorb things for 8 hours straight, so I digress. Do you want to see some pictures? Why not, right? I made them. So this is a different kind of picture here. X-axis is time-varying stress. Y-axis is disease severity. Pick your favorite disease. We're going to do an example with psoriasis again, but you can pick something else that stress is supposed to exacerbate. So each of these lines is a trajectory for a different kind of person. So the blue line is for somebody who has a mean level of stress of 6. The green line is for a mean level of 5, and the red line is for a mean level of 4. So sometimes they have more stress, sometimes they have less, but this is their average in the middle here. And what this picture shows is a result that would make any longitudinal design researcher cry. This is a result that says the only relationship between stress and severity is between persons. That's shown by the slope of the yellow line through the means. For every unit more mean stress, your mean severity goes up by 1, the end. Whenever you have more stress than usual, whenever you are further over on your own line, there's no change in your severity. So this result would mean that it was a total waste of time to collect these things longitudinally, because you could have found the same thing if you had measured them once. Now, you could try to spin that total lack of within-person relationship into a story, right? I mean, if you could make a null hypothesis a story, then maybe it's not a waste of time, but this would be disappointing. In contrast, this one, camera 1, camera 2, camera 1, camera 2. Please tell me you understand that reference. Yes. I'm not that old? Some of you are like, I am that old. It's called Wayne's World. You can ask the Google about it later. Make sure you watch the part where they're doing Bohemian Rhapsody in the car, because that's another cultural point you need to understand. Anywho, 1, 2. So this is the opposite pattern. Now, no between, all within. It's not that people who have more stress than other people have worse severity, because the yellow line through the means is flat. It's that when you have more stress than usual, your severity is worse than usual. Totally within person effect. Now this would be exciting. Or you could have some combination of both. So this is a between person effect slope of 2, the slope of the yellow line through the means, and a within person effect that has a slope of 1. So now people who have more stress have worse severity, and to a lesser extent, when you have more stress than usual, you have more severity than usual too. Now these lines are parallel. They don't have to be. Here's a picture that's coming here where they're not parallel. How do I get them not parallel? Interaction terms. So what if we added interactions? Is it possible that your reaction to having more stress than usual depends on just how much stress you have? Is that possible? At some point, is it like more? It's like, bring it. Like, it's not going to bother me anymore. Yeah. To get at that kind of idea, you can make an interaction of the two pieces of these variables among themselves, an intravariable interaction. So I've added to my within person effect here, I have added a cross-level interaction with person mean x, and I've added a random slope here. So I would do these in the same order as usual. Once you have a fixed effect at level 1, like we used to have a fixed effect of time, we can test to see if it's random. That's a likelihood ratio test. That's the addition of this U1 here. So what does a random slope, what did it used to mean when we talked about time? Random means what again? Everybody gets their own. So if we're talking about time slope, then everybody gets their own rate of change over time, right? Say that again? No. What?
How much do you differentiate from your own line?
That's residual. Like E is how far off from the line that you've been given you are. How far off your line is from everyone else's, that's random. You can say it that way, yeah. In this context, what does a random slope mean? It means the same thing, you just can't think of it as a slope of time. It's a slope for within person x. So what do people get their own of now? Their own starting point or their own mean is carried by U0. That's the random intercept. So if this were severity, some people have worse disease severity than other people, sort of on average. But if we have a within-person relationship here, let's call it between X is stress and Y is severity, within-person effect of stress on severity. Within persons, that's the idea that if I have more stress than usual, my severity is worse than usual. So that's the fixed effect. So if I make that random, then I'm saying the extent to which stress affects me The extent to which within-person stress affects within-person severity varies over people. Some people are more reactive. So you can think about within-person changes in stress and severity, the extent to which they go together. That extent varies over people. For some people, having more stress than they're used to really sets off their disease. For other people, there's no effect. And I'm hypothesizing here that part of the reason why some people are more reactive than others to within-person stress is their average level. And that idea might show up as a picture like this. So this picture has a simple effect of between-person stress here. The slope through the yellow lines is specifically when within-person is 0 is 2. The simple effect of within-person stress is specifically for this green person. They have a slope of 1. And for every unit higher mean stress, this within-person slope becomes less positive. It's a negative interaction by 0.5.
So here the average level is moderate.
The average level is the moderator. So I think of this as like maybe the difference between undergraduates and graduates. Can I make fun of undergrads? Is that okay? Why not, right? It's like, do you remember what it felt like to be 18 when everything was a big deal? It's like, oh my God, I have chapped lips. This is the worst. People who don't have a whole lot going on necessarily, maybe a little more reactive at the time you're up there on the blue line, and it's like, my car won't start, my baby's sick, my report's due tomorrow, oh, and I just found out that my has lice, right? Bring it! So that's just, a hypothetical, but the idea that you may be more reactive or less reactive depending on how much you have to react to. That would be a within-person by between-person interaction of the same variable. So the thing that you can't do, the thing that everybody does without realizing it, is to put only one term in the model right here and call it good. It would be the idea that there's only one slope to be had here, and you just try to bend it through all this stuff at the same time. Is there? Yep, thank you. Yes, this needs to be a 1-1 right here. Thank you for catching that. This one right here is a 1-1. I think this is not, oh, good, I can fix it. Let's see, I didn't know if that was a picture or not. There we go. Thank you. There, that's better. All right, so we can look at this type of effect here in the context that I've been using as an example with a real-world example. So I have example 3A for you here. Now I told you about this story last semester. I tell lots of stories, so I will bring up the picture again to remind you what the story was. This one, it was example 4. Remember this picture? The story behind this picture, this was these are real data from a grad student at KU who walked into her dissertation proposal with a nice happy cross-sectional study looking at how the effect of stress on severity was moderated by personality and forgiveness and coping and stuff like that. And she walked out with a longitudinal study too. So I helped her analyze these data. I went to, when I was at Penn State as a postdoc, we had something called Methods Lunch, which I had tried to start here and had failed miserably, so we don't do it anymore. But the idea was that if you're working on a data analysis problem and you want advice, to bring it to the room and everybody would sit and talk to you and eat their lunch. And I brought these data because I wasn't sure what to do with them. Because in this context, I wanted to know how stress and severity were related, but I knew it wasn't a growth model because neither one of them were growing. It's like, so I think it's like, it's multi-level, but there's no time and I don't know what to do. And it was Mike Rovine, who just recently retired from there. He said, well, it is a multi-level model, just don't put time in it. Like, you can do that? Yeah, you can do that. So this is what we ended up doing. So this is psoriasis severity across 7 weeks of data. People just reported on their psoriasis. This wasn't a treatment study. And this is what the individual data look like. Here's the mean line. So there's no change on average. And as you can see, there's very little change within most of the people, a few exceptions, of course. And the interclass correlation for that outcome was 0.83. So what does that mean? Interclass correlation of 0.83. Say it together. 17% longitudinal, 83% waste of time. Yeah, committee. But you know what she did? Can anyone guess? Wrote it up and turned it in and graduated. That's what she did. Let that be a lesson. No matter what happens, you shall write it up, turn it in, and graduate. So here's the setup for her data. I originally had what is known as a wide or multivariate data set. So I was able to calculate a person mean across her stress variable. It was a measure called the LES, Life Experiences Scale, something like that. So across the original 8 columns, I created a person mean using the mean function in SAS here. And then I stacked the data. The severity measure was called SAPASI, and I do not remember what that means, but it's the measure of severity that we have where more is worse. And so the variables then that we're going to be working with, I have selected only the rows where I have both measures, so only complete occasions in the data set here to keep the sample the same. I have person mean stress minus 2 because 2 is near the mean for this particular measure. That person mean stress minus 2 is a variable I'm calling between person stress here because it's differences in average stress level as a predictor. And then the original time varying stress minus the person's mean has been person mean centered, creating this new variable that I'm calling within person stress lag 0. So within person stress, the idea of whether or not you have more or less than your average level, whatever that happens to be, lag 0 meaning that same week. So part of her hypothesis was that it takes time for the effects of stress to show up on your skin. Psoriasis is a skin condition that's supposed to be exacerbated by stress. And one of the things she wanted to look at was to what extent the effects were contemporaneous versus took time to happen. So to get at this took time to happen idea, we computed 2 new variables. Now I used to have a whole bunch of extra code in this example to create lagged variables, and I think it was about this time last year I discovered this proc expand, and I almost cried because it's so much easier than the code that I had written. But this thing is awesome. Proc expand can do anything like sequentially in a file, like it can do moving averages, it can do lags, it can do sequential differences, it can do anything like that, and it can do it for multiple types of ID variables. So this command here takes my original within person stress variable and saves it as a new one where I've lagged it 1 unit, and I did the same thing to test a 2-week lag, and that creates a data file that looks like this then after you're done. So here's subject 100, here's their 8 weeks of data. We have a severity score for this person at each week. Here's their person mean stress that's copied down across all the columns. That's what you want. It's time invariant. Here's the centered version of that, which is person mean stress minus 2. That's what's going to go in the model. Here's my original time varying stress. Here's time varying stress minus person mean. So like for instance, this person was lower on stress than usual the first 2 weeks, but they were higher than usual on week 3. And then the lags take these values and shove them down one column so that week 1's stress predicts week 2's severity. And for the lag 2, week 1's stress predicts week 3 severity. And so we're missing the ones at the top here where we didn't have the previous occasion to lag into. And this proc expand is smart, and it doesn't allow us to lag into the next person. So it doesn't take the last observation from person 1 and put it as the first observation in person 2. It understands that. Whereas writing code to make that happen was a lot more code, and so that's why I was so excited when I saw this thing. So that's the story. Does stress predict disease severity, and does it take some time for that to happen? A lagged effect logically can only happen within persons, right? Because it has to be relative to where you normally are this time versus next time. All right. Are you with me? You want to see what happened? Yeah. So, first stop here. Empty means random intercept model for severity as my DV. How much of it is between versus within? So I got VCore, by the way, is where you can get your interclass correlation without having to do math. If you want to calculate it, it's random intercept over random intercept plus residual variance. And so 0.83 indicates 83% between, 17% within. So the best case scenario is that she has 17% of the data to address these hypotheses about lagged effects. I did the same thing for stress as my time varying predictor to see how much variance is between versus within, and I came up with an ICC of 0.56. So that means that we do have to worry about a potential between effect of stress and a potential within effect of stress. The best fitting unconditional model for time that we ended up with at the end of example 4 in the previous class looked like this. It had a random intercept. A random intercept says that we have a constant correlation across time. In addition to that, we had different variation at each week and 3 lags worth of Toeplitz correlations. So weeks up to 3 apart had an additional correlation of their residuals over and above this random intercept. This was the model that through nested model comparisons fit relatively best, not worse than unstructured. The only predictor that I have in this model is person mean stress at this point. Time's not part of the story. Time doesn't need to be part of the story. Whether or not time belongs in the model is something you would have already tested at this point. So there was no fixed effect of time. There was no change on average in psoriasis severity during the study. So we don't need a fixed effect of time. And because there's no systematic change, a random effect of time wouldn't have done us much good either. So this is an instance in which an ACS, alternative covariance structure model, would work better. So I have 124 subjects, 8 observations per subject at max. I had already selected the data so that all observations had to be complete to be part of these models. That's why I have 880 cases. Not everybody has complete data. And here's where we go. So here's my fixed effects. 1.9 is the average psoriasis severity when? So I know what you're going to want to say. What do we normally say? Time 0, right? Do I have a time 0? No. So at any of the weeks, 1.9. For what kind of person is psoriasis expected to be 1.9? Yeah, for somebody who has a mean stress level of 2. For every unit higher person mean stress, severity on average, the whole set of 8 weeks, goes up by 0.45. So this is a cross-sectional effect. This is a between-person level 2 cross-sectional effect. It describes differences in mean psoriasis severity as a function of differences in mean stress as taken across the 8 observations for a person. I don't have the variance components on here because we're focusing just on the fixed effects for now, but which kind of variance should person mean stress have accounted for? Is person mean stress a people thing or a time thing? People thing. People are level 2, so which kind of variance should person mean stress a people thing at level 2 account for? Random what? One more word. I heard it. Intercept? Yeah. Yes. Random intercept. That thing. Now here is, I have my equation over there. Now I'm adding my within person effective stress. So the equation right here, if you have somebody who doesn't like to read the words in your study and they prefer equations, this equation, now that word sounds funny, equation. Did I say that wrong? Equation. You ever say a word so many times it sounds weird? It's macabre. My equation is macabre. That equation says person mean centering. That's what that says. I have a lag 0 stress TI in it as my level 1 predictor minus person mean stress. So the bar over it means mean, and the I means it's a person mean. So that tells me right there that this is a within person effect using only within person variation in stress. Between person stress then goes in the level 2 model right here, and it is person mean stress minus 2. Here is my beta 1 placeholder equation at level 2 for the within person effective stress. The fact that there's only this one gamma here tells me what? What are we assuming about the effect of within person stress right now? It's one thing. Like everybody gets the same, right? Everybody gets whatever this number is. We call that, give me an F. Fixed. Yes. Fixed effect. All 8 observations are used because this is a fixed effect of lag 0 stress, contemporaneous stress. And survey says, wah, wah. So the coefficient is tiny and negative and non-significant. So for every unit more stressed you are than usual, your psoriasis severity goes down a tiny bit, 0.07 per unit, 0.007 per unit. So far no hypothesis to support within-person effects of stress and psoriasis. But that's okay. What if it takes time? So I have added lag 1 stress as a new predictor, and I have given it a fixed effect. Now this is a point where reasonable people may disagree, and I will give you my opinion, and you can decide for yourself if you agree with me. Whenever people have these kinds of hypotheses about lagged effects, you see these sorts of like pathy models that look like this, you know, this variable predicts this later on and this one predicts that one. To me, I don't think you can say that there's a lagged effect until you control for the contemporaneous effect. To show that it really is 1 week later that matters, I want to see that 1 week later above and beyond 0 weeks. That's my opinion. And the models that do this without controlling for contemporaneous effect to me are problematic. So even though this is non-significant, because I want to be able to say that it's really 1 week later that matters, I'm leaving it to be controlling for contemporaneous effects. That's me. So I have within person stress lag 0 and within person stress lag 1. And note what happens to my sample size. Now I only have 7 observations max per person. Did I do something wrong? No? Amy shaking her head, no. Why am I okay? I don't have the first one, exactly. I don't have the stress that happened before the study started by which you would predict week 1 severity. So that means these 2 models, the contemporaneous 0 lag model and the 1 lag model here, are not being run on the same samples. So that isn't necessarily a problem, but it would be a problem if I did any kind of -2 log likelihood comparison. -2 log likelihoods, AIC and BIC, are all sample specific. They have to be done on the exact same samples to be comparable. So I'm not going to use any of those statistics. I'm just going to stare at the p-values. Survey says, dun, 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 dun. I got something. So we still have a between person effect. For every unit more person mean stress you have at level 2, your psoriasis severity mean goes up by 0.48. And for every unit more stressed than usual, your psoriasis severity the next week specifically goes up by 0.059. So stress is bad for you. It would be tempting to look at these numbers and say, well, the between person effect is way bigger than the within person effect, right? But these are unstandardized coefficients. So to be able to interpret what they actually mean in terms of a comparable effect size, I'd have to somehow standardize them so that each of them has the same standard deviation with respect to X and Y. So these numbers will only be comparable if both X and Y have exactly the same amount of variance between as within. If both of them had an intraclass correlation of 0.5, then they're on the same scale. Otherwise, they're not. So I made a picture, and I gave you the Excel sheet that made the picture. This is how I would show this type of within person and between person set of effects. I have an x-axis that is not time. Time is not in my picture, even though this is a longitudinal finding. My x-axis is previous week's stress, where average means my average, and below average versus above average. To figure out what those would be, I took plus or minus 1 standard deviation of this variable, which worked out to be actually 1. So the slope of these lines shows the within person effect of stress. When you have more stress than usual, your psoriasis severity is a tiny bit higher. The vertical distance between these lines shows the between person effect of stress. For every unit more average stress, your average psoriasis severity goes up by the coefficient. And so these are, again, plus or minus 1 standard deviation of the between person variable. Questions? Now, what do you notice about those lines? They look nice and orderly, right? Like parallel even? Why are they parallel? Did I screw up my graph? I have a fixed effect. Would they be non-parallel if I had a random effect? They would not, because these pictures are showing fixed effect predictions. The reason that they're parallel is because there's no interaction in this model. There's nothing in the model that says the within person effect varies by the between person variable. I could have that, but I didn't. I believe it's non-significant, though. I'm pretty sure I looked at that at some point in life. I tried lag 2 in addition to lag 1, and it was not significant. So lag 0 was not significant, lag 1 was significant, and lag 2 was not significant. So there, her committee gave her one p-value to write up. Now you'd have to judge for yourself whether 8 additional weeks of data collection is worth one p-value. I'm not sure what the going rate is, but to me that doesn't seem like a good deal. But what do I know? So you know how the model for the variance part is the part that you don't give a crap about, like all this topolits and everything, like that's not the part you designed the study to answer? I wanted to show you what happens if you decide not to give a crap about that. So here is our lag 1 model, the resulting coefficients and standard errors under different variance models. So unstructured, that's the best possible model, right? It uses the most parameters, but it's the most exact. It lets all the variances and covariances across weeks be whatever they want. So here's my coefficient, here's my p-value. Here's the one that we decided on as being not worse than the best possible model. Here's my p-value, still significant by a considerable margin. What if you're like, I don't know, so I heard once in a book about AR1, I'll just throw that one in there. Similar fixed effect. P-value is creeping up there. How about, let's just throw in a random intercept and be done. P-value is creeping up there. And the worst one, VC. Now, why is that one so much different than the others? Coefficient's fairly similar, but the standard error is like 4 times the size, relatively speaking, and the p-value has the consequence. Why is VC so much different than all these other ones? No one remembers. What's VC stand for? Variance components. What's it called in other programs? Diagonal, independent. Does those words ring any bells? What's VC predict? What's the pattern? Nope, worse than that. Zero correlation. VC is an independent structure. It says equal variance over time, no covariance whatsoever. It's a one-pile E-only model. That's what VC is. Compound symmetry is the same thing as random intercept only. That's why I have a CS here in parentheses. So random intercept only says there is a covariance across time, but it's the same one. AR says the covariance declines exponentially as a function of how far apart in time they are. Here's the model that we picked, and here's the right answer. So the ones that have the significant p-value are the ones that somehow incorporate the dependency of weeks from the same person. VC doesn't. If you go back to the idea of dependency being represented via piles, do you remember how much of the data was between person to begin with? What was the interclass correlation for severity? 83. So 83% of the variance in my outcome could not ever have been predicted by within-person stress. This VC model don't care. It puts between and within together to build a ginormous standard error, and that's why the p-value is so different. Because it's not differentiating which kind of variance a within-person effect could possibly predict. Within-person variance should only predict E-variance, right? And that's why all of these other ones look so different. So there's much less of a difference once you start fussing with what kind of dependency you have, like these ones here, and then just ignoring it altogether. But had she run this as a typical regression model, using stacked data, assuming independence, she wouldn't have found anything. So that's why you're here. It makes it better. Okay. So big picture, we're talking about time-varying predictors. Why are time-varying predictors complicated? It's in the slides. Why can't I just put my time-varying stress in the model and be done? Because it's both within and between. What do you think I'm doing when I put it in the model and be done? What am I assuming? Any guesses? Nope. That's a good guess. If I have two effects hidden in something and I only allow one, what do I have to assume about the two effects? They're the same. If I just put in time-varying stress and I'm done, I am assuming that the between-person effect and the within-person effect are exactly the same because I've allowed them only to be represented by one parameter. So in this example, for instance, I would be saying that 0.48 and 0.05 are the same number. Now I can write an estimate statement right now to test the difference between the two of them, and it's probably going to be significant. It's going to be significant for several reasons. Number one, they're not on the same scale. Each of them has a different standard deviation in X and a different standard deviation in Y. Number two, they mean different things. The reasons why some people have more stress in their lives is different than the reasons why some days have more stress in them. Conceptually, theoretically, they're different. So more often than not, these things will be different numbers, and to put in only one variable smushes them together. And that's the problem. Now, why do I say that these are for fluctuation? Well, go back to our growth model piles of variance, right? Once upon a time there was an E, one circle. Then we split it into two circles, U0 intercept variance at level 2 and what is still E, a little bit smaller now. Here's 2, here's 1. We put in fixed time and explain some of the E, and then we put in random time, and then random time splits into what is now another type of level 2 variance, U1, and what is still E, smaller at level 1. So there's 3 piles, right? And if I added like quadratic time, I could do it again, right? Make more piles. So what we've talked about thus far is really only the E and the U0. By building person mean, we're trying to make an observed variable version of U0, and by doing within person, we're trying to make an observed variable version of residual. But what if we have change? How do we carve up my predictor to represent individual differences in the mean, individual differences in, say, a slope over time, and residual variance? You can't. And that's the point at which you need a multivariate model instead. Even if you're thinking of your time-varying predictor as a predictor, it has to be considered an outcome from the perspective of the model so that it can find each of these variance components. So this sort of on the cheap and easy brute force box way of doing things, if you have time-varying predictors that have individual differences in change, you cannot do this. It will not work. That's what the beginning of chapter 9 in my book shows. It was actually based off of a long-standing argument with some collaborators at Penn State, and I did a little simulation that demonstrates pretty unequivocally that if you try to carve up your predictors into boxes when there's individual differences in change, it ends up that whatever relationship you would have had between the slopes and between the residuals gets shoved together. It's a different kind of smushing that is still smushing. So for the same reasons that when you're building a model for an outcome, we try to figure out what piles of variance it needs, you have to do the same thing when you're thinking about a predictor that's measured at level 1. Now whether you have another variable, let's do my circles for some other variable over here. Whether you're thinking of it as this variable predicts that one or it goes the other way, that's up to you. But the idea is that you're letting the model find the variances, and those variances then are what carry the effects, the relationship between variables. Okay? Okay. So today's Wednesday, that means you don't get to see me for 5 days. I hope you're okay. So have a good rest of the week. Let me know if you need help with homework too, and I shall see you on Monday.